Okay, this is the next lecture on, and I'm trying to slot this in between two that I've already done, and I want to slot this in between them because I think this sort of misses out on some crucial steps in this quest towards what is mass. So let's just go over some of the things. Let's just put this here, molecules. Okay. Molecules. All right, so some of you who know a bit about this would have picked up a mistake that I had on the board, and thankfully he's not around. And his name is Niels Bohr, and I had that spelled incorrectly. So I had that spelled as B-H-O-R, and in fact it's B-O-H-R. So I hope his ghost will forgive me for doing that. Okay, now, so what is mass? This is lecture 1B, if you like. First of all, let's go over what are atoms, the smallest part of a single element, and elements are those things that you can see on a periodic table. So if you're actually interested in this subject, then I urge you to print yourself off a periodic table and have a look at it. And in a subsequent lecture, I'll go over the periodic table and I'll explain how it works, what those things mean, what do those symbols mean, and what do those numbers mean. So I'll explain that in another video. But anyway, for this particular series of videos, we're having a look at trying to work out what does mass mean. Mass is something that's used right through our universe, intrinsic part of gravity, for instance, and our understanding of why things fall have all got to do with mass. So let's see if we can work out what it is. Now, this is rather simplistic, if you like, look at what mass is. But anyway, I think it will give you a general idea, and I'm pretty sure it covers it quite well. We could go into special relativity and general relativity and complicate the issue a bit, but I don't think that's necessary. I think this covers it quite well. So let's proceed. Okay. Right, so the other thing is that we know that the number of protons defines the elements. In other words, the difference between one thing and another is one element and another is really comes down to the number of protons that it has. Okay, a neutral atom has equal a number of protons and electrons. So, as we discussed in the previous, go over the other video, and you'll see that atoms are predominantly, all of them are made of a central nucleus of protons and neutrons, and then in a cloud around it, if you like, with a high probability of reaching a particular radius, we have electrons. So protons are positively charged, electrons are negatively charged. Okay, so all elements except for hydrogen have neutrons. Okay, so that's hydrogen 1, as in the lightest element being hydrogen, having 1 proton and 1 electron. As I said in the other video, you can have other variations on hydrogen. You can have heavy hydrogen, so such as deuterium and tritium, that have neutrons as well as having protons. Okay, so neutrons have the same size and density as protons, so for all intents and purposes, the same stuff except neutral. They don't have a charge. An example, let's look at this one. Nitrogen has 7 protons, it's got 7 neutrons and 7 electrons. So 7 protons, electrons and neutrons. And the mass, so we're talking about mass now. Remember, if you had a look at the previous video, and certainly the one that's coming up, you can have a look at these videos. And the mass of, in other words, the stuff, the total amount of stuff, that's the amount of protons and the amount of neutrons together, which make up the mass, okay, of of 6.02 by 10 to the 23 atoms of nitrogen. You've got 7 protons, 7 neutrons, that comes to 14 grams. So if you have this many of them, they will add up to 14 grams. So that constitutes what the mass is. Okay, so for an example. Another example, mass of this many, 6.02 by 10 to the 23 molecules of nitrogen. So nitrogen doesn't go around as N by itself, even though the element N, nitrogen goes around in molecules. In fact, there's 5 gases in particular that go around like that. So hydrogen, nitrogen, oxygen, fluorine, and chlorine. Okay, those 5 reactive gases will go around in pairs like this. Okay, so they are highly reactive and they could never appear in nature as, say, for instance, O on its own. It would always be O2 or O3. Okay, in the mass of 6.02 molecules of carbon dioxide, for instance, that's carbon dioxide is carbon plus 2 oxygens bonded together. In other videos I'll show you how this bonding takes place, but nevertheless for this video is about the mass, so let's just stick to that. 1 carbon atom, 2 oxygen atoms getting together. The 1 carbon atom would be 12 grams for this many of it. The 2 oxygen atoms for this many would be 32 grams. So there's 2 of those oxygen. That's 16 each. Comes to 32. So 44 grams for this many. So if you think about this many, that's 44 grams. To give you an idea, in just normal temperature and pressure, so at about 20 degrees Celsius and at sea level, so 101.3 kilopascals, you'd have about 24.4 grams, 24.4 litres, okay, 24.4 litres of this carbon dioxide would add up to 44 grams, okay, so 24.4 litres. So, sorry about that mix up. 6.02 by 10 to the 23 molecules of carbon dioxide at 20 degrees and 101.3 kilopascals, so about sea level, would need 24.4 litres of that gas. Okay? Alright, so to give you an idea of nitrogen, if we wanted this many, if we had that many atoms of nitrogen, and the pressure was 101.3 kilopascals, so at sea level, and we had this many and at sea level, and the temperature was 20 degrees, then we would have 28 grams. So you can see carbon dioxide is, considerably much more heavier than nitrogen. And if it was oxygen, then we'd have O2, and so oxygen is 8 plus 8, so 16 grams for just oxygen. So oxygen as a molecule, so O2 would have 16 times 2 would make it 32 grams. So again, at 20 degrees and 101.3 kilopascals of pressure, we would end up with 24.4 or thereabouts litres of oxygen would fit. That's how much space it would take up in terms of volume. Okay. All right. So the main thing here is what we want to get across is that the mass means the amount of this stuff and this and neutrons. Okay. So it's this and this makes up the mass, if you like, of the stuff, and you can equate that back to the number of them there are. So if you think about mass as being the number of protons and the number of neutrons, think about that as being the mass. If you want to know exactly what the mass, in other words, if you calculate it back for a particular one, then for a particular proton you could quite easily do the math for that, and because you know that it's 6.02 by 10 to the 23 as the number of them. Okay, if you do that with 7 protons and 7 neutrons each, you can work that back and work out exactly what is the mass of one proton. Now, I've left that up to you because it's a bit of fun to do, and but if you like, in a later video I will discuss the mass of protons, and I'll even discuss the mass of electrons. Okay, I think that's probably about enough for this one. I think the main thing is for you to understand that molecules, the difference between an atom and a molecule is a combination of atoms. It could be the same element together, so N2, O2, F2, Cl2, I2, for instance, iodine, and then in gases like CO2 for carbon dioxide, CH4 for methane, and so on, C3H8 for your propane, C3H8, yes. Okay, so basically you can work out what the mass is for a particular molecule. Okay, and we're talking about this many. And by the way, there's a word for this 6.02 by 10 to the 23. If we put that many things together, and I can't remember if I said that in the last video or not. If I didn't, then you've got it here, and this is called a mole. Okay, I'm pretty sure I did mention it. So a mole it refers to this many of anything. So if you want to know how many cars do you get in a mole of cars? 6.02 by 10 to the 23. How many pens do you get in a mole of pens? 6.02 by 10 to the 23. How many atoms of hydrogen are in a mole of hydrogen? Okay, 6.02 by 10 to the 23. Now, hydrogen is one of those that go around in pairs, as I said, and you've got one proton, no neutrons. Okay, so with your one proton, let's assume that this hydrogen doesn't have any isotopes with it. Okay, so I know there'll be some in there will say no, it won't be exactly 1, because it'll be 1.008, because that's the average. I need to do another video if we're going to cover why, specifically how those isotopes work, how we average those isotopes out to get a number like 1.008. But let's say that our hydrogen was quite pure and it only had this one isotope in it, then we'd have just one proton for each one. So if we've only got one proton, and 6.02 by 10 to the 23 of those protons just adds up to 1 gram. So let me go over that again. One proton, 6.02 by 10 to the 23 of these protons is equal to 1 gram. You can pretty much work out how much a proton is. Have a bit of fun with the maths and do that for yourself. Okay, now hydrogen goes around in pairs, so therefore 6.02 by 10 to the 23 molecules of hydrogen, so that's any hydrogen that's going to be floating around you is going to be as a molecule in pairs, in H2, and so therefore there'll be two of them together, and therefore that will be 2 protons. So 6.02 by 10 to the 23 molecules, that'll be 2 protons, so therefore they'll have a mass of 2 grams. Okay, so this many protons by 2 of hydrogen molecules will be just 2 grams. So you can see how light that is. Now, as we know, helium is one of those things that floats, and of course, you know, because people make helium balloons and the like, and of course it would float a lot better if it was, well, twice as well. It would have twice the buoyant force if it was hydrogen than if it's helium, because hydrogen is only well, it's not twice actually, it's about 4 times as much. So hydrogen is a lot lighter. So let's have a look at what if it was helium. Helium's got has got 2 protons. Helium's got 2 neutrons as well. So that makes 4. Okay, so that means if I have this many atoms of helium, then I'm going to have 4 grams. Okay, so that's considerably more than hydrogen, actually 4 times as much as hydrogen, not double, 4 times as much as hydrogen, the atom, twice as much as hydrogen, the molecule. So obviously hydrogen is a molecule when you put it in a balloon, so that would be 2 versus 4, so that's where the twice as much comes in. But if we're just looking at atoms, atom of hydrogen, atom of helium, then we're looking at 4 times the difference. I hope that's that got across all right. Okay. All right. So watch the if you're interested in me doing more of these or posting more of these, then just hit the subscribe button. If there's enough of you, then I'll do that. If nobody's watching them except my students, we're going to move on to a different platform. So my students will probably get to see. Well, they will get to see my videos in a different platform, but that's not publicly available. So, so if you're interested in stuff for me to do and post my lectures in public, then I'm happy to do that. But only if there's some interest there, obviously. I'm very busy. Okay, so if that is the case, then press the subscribe button and also press that little bell, and then you'll know when I'm going to post another one. On this, what is mass? There's 3 in this series. So there's one L1B, and then there's an L1 and L1B, and then there's an L2. And I think by the time we get to L2, we pretty much nail what is mass. Okay. After that, I'll do some more videos with respect to mass and also matter, and then we'll have a look at an interesting look at how gravity works. So in other words, we'll be discussing Einstein's general relativity and how Einstein had a look at gravity, and then we'll be able to have a look at what Newton did and see if we can bring those 2 things together and make, if you like, the idea behind general relativity something more accessible to the general public. So without going into all of the mathematics and that, try and make it more understandable, and to see how we can say, if you drop 2 things, for instance, they fall at the same time, how is that represented in Einstein's model? So that's easy to understand in terms of Newton's model. You know, they both fall to the earth at 9.81 meters per second squared. That's the acceleration due to gravity. So if they both both do that independently of their mass, then we pretty much know, can explain that with Newton. That's quite easy. But how do we explain that in terms of these two things falling? How do we explain that in terms of Einstein's general relativity? I'm going to have a look at doing that. I bought this little ball on it, and we're going to try and use that and see how we can actually do that. That should be quite exciting to do. All right, thank you very much for listening. Once again, if you want more of these, then press the subscribe button and also that little bell, and you'll know when I'm going to post another one. Thank you.